Welcome to the Deep Dive, where we cut through the noise to get you truly well-informed. Today, we're plunging into a topic that has fundamentally reshaped global energy: hydraulic fracturing. Think about it. In less than a decade, this technology transformed the U.S. from a major gas importer to becoming self-sufficient. That's not just an engineering feat. It's a technological revolution with immense real-world consequences, impacting everything from geopolitics to, well, maybe even your energy bill. But here's the kicker, and this might genuinely surprise you. Despite its monumental success, a significant chunk of these hydraulic fracturing efforts aren't nearly as effective as they could be. We're talking about an average of 29.6% of hydraulic fracture clusters that simply don't produce any oil or gas. Imagine that. Nearly one-third of every attempt yielding nothing. That's a staggering waste of investment, resources, and time. It's sort of the silent killer of profitability in the fracturing world, and it's precisely what this new research we're looking at aims to fix.
It's an enormous challenge, yeah. And the core of it really lies in the incredibly complex three-dimensional behavior of these fractures, especially in their earliest, most critical stages. Current assumptions often simplify this complexity way too much. They imagine fractures growing in these neat, predictable patterns. But the subsurface is rarely, if ever, neat. It's a dynamic, unpredictable environment, and this is precisely where advanced simulation techniques come into play. They help us sort of see what's happening underground.
And that's our mission for this deep dive. We're going to explore some cutting-edge methodologies, specifically a 3D Generalized Finite Element Method, or GFEM. This was developed by researchers Shauer and Duarte. We'll unpack how this method offers a crucial shortcut to understanding the often unseen and, frankly, surprising dynamics of hydraulic fracturing, revealing insights that promise to make this vital process far more efficient and reliable. So how do we begin to unravel this underground mystery? Let's really dig into this challenge of low production first. What are the traditional assumptions we often make about how these fractures grow deep beneath our feet, and where do those assumptions fall short when confronted with the gritty reality of the subsurface?
Well, the common mental image, and often the simplified model you see, is that hydraulic fractures propagate neatly, perfectly perpendicular to the wellbore, and that they remain perfectly planar-like a flat sheet of paper pushing through rock. You see this in introductory diagrams, right? And it's a useful starting point for theory, I suppose. But the reality is just far messier. Factors like the influence of neighboring fractures and, critically, the in situ stresses, that's the natural stresses already present in the rock, they can significantly alter a fracture's orientation. They can lead to what's called tortuosity.
Tortuosity. So
Yeah.
if I'm picturing this right, the fracture isn't just a straight line, but literally twisting and turning, like a corkscrew kind of, as it tries to navigate the rock.
Exactly.
And that's what can lead to failure.
Precisely. Imagine a very narrow, high-pressure pathway trying to maintain its integrity while twisting and turning like that. This tortuosity can significantly increase friction, reduce fluid flow, and sometimes even cause the entire hydraulic fracturing treatment to fail prematurely. The fluid just can't effectively get where it needs to go, or the pressure isn't distributed correctly.
So for you, our listener, why does this complex, twisty-turny 3D behavior matter so much for the efficiency and ultimately the success of a fracturing operation? What's the real-world cost of not understanding it better?
Because quantitative predictions of this precise 3D geometry near the wellbore and its subsequent impact on fracturing pressures remain what many in the field call an open problem. Think of it this way. If you're trying to hit a target deep underground, but you don't accurately know exactly where your projectile is going once it leaves the barrel, well, you're essentially shooting in the dark. Without accurately predicting these intricate shapes and how they affect fluid flow and stress distribution, we're working with an incomplete picture. It's guesswork. This directly explains why we have that frustrating 29.6% of non-producing clusters, and it significantly impacts the overall economic viability of drilling operations. We're talking potentially billions of dollars in losses and missed opportunities.
This is where it gets truly compelling, I think. To tackle these mind-bending 3D complexities, this shooting in the dark problem, researchers are turning to incredibly powerful computational tools, like the Generalized Finite Element Method, or GFEM. What makes GFEM particularly suited for simulating something as dynamic and intricate as growing hydraulic fractures?
Well, the core advantage of GFEM for fracture problems is actually quite elegant. Unlike older methods, the computational grid representing the rock, what we call the solid mesh, it does not need to perfectly fit the fraction.
Okay.
And this is absolutely crucial because, as we just discussed, real fractures can develop highly complex, non-planar, even erratic shapes. shapes that would be incredibly difficult, if not impossible, to perfectly remap onto a traditional computational mesh at every single step. Imagine trying to perfectly resculpt a detailed model of a growing, twisting crack every microsecond. It's just hugely inefficient computationally.
Right, that sounds like a nightmare.
Yeah.
Yeah.
So GFEM achieves this remarkable accuracy without that constant resculpting by using clever mathematical tricks we call enrichment functions. These are special mathematical capabilities added to the standard computational elements. They allow the computer to precisely model sudden breaks and sharp edges, like a growing crack within the existing grid structure, without needing to perfectly redraw its entire virtual rock structure every time.
Okay, so it's like having a smarter tool that adapts.
Exactly. It's like having a super sharp chisel that automatically adjusts its cut to the contours of the break, rather than needing a whole new block of stone each time. And to keep things computationally efficient without sacrificing accuracy, the methodology also employs something called mesh adaptivity. The mesh automatically refines itself, adding more detail right around the fracture front at each propagation step as the crack grows. And then it intelligently unrefines later where that high level of detail isn't needed anymore. It's a very smart way to save computational power.
Very clever. So when we're talking about the fundamental physics here, how are the rock and the fracturing fluid actually characterized in this model? What are the key properties you're working with?
That's a great question. For the rock itself, we model it as a 3D isotropic elastic material. Think of it as behaving uniformly in all directions under stress, which simplifies the immense complexity but still captures its essential elastic response. The fracturing fluid, on the other hand, is modeled as a Newtonian incompressible fluid. This means it behaves consistently and predictably, and its flow is governed by Reynolds lubrication theory, which is pretty standard for describing fluid movement in narrow gaps like inside a fracture.
Okay, that makes sense. Understanding how fractures grow within the rock is one thing, but how the fracturing fluid actually gets into multiple fractures from the wellbore, that seems like another critical piece of this complex puzzle. How does this GFEM methodology account for that dynamic fluid flow from the wellbore and its precise distribution into the various fractures?
Yeah, a proper estimation of how the injected fluid partitions itself among multiple fractures is absolutely paramount for efficient operations. It's critical. If too much fluid goes into one fracture and too little into another, you're just not optimizing your recovery, you're leaving resources behind. So this methodology models the wellbore itself as a 1D domain, which is a crucial simplification that works well because the flow within it is primarily axial, along its length. It then uses the Hagen-Poiseuille relation for laminar flow to describe the fluid movement along the wellbore.
Okay, a 1D pipe, basically.
Essentially, yes. And the clever part is how it couples the wellbore to the fractures. At the perforations, those small holes drilled in the wellbore casing that allow fluid to enter the rock. A sharp-edged orifice equation models the pressure losses. That's as the fluid moves from the wellbore into each individual fracture. Then, 1D connecting pipe elements are used to link that 1D wellbore model to the 2D fluid mesh within the fractures. What's particularly ingenious about these connecting elements is their efficiency. They add very few degrees of freedom to the overall coupled system. So it keeps the computational cost down while still accurately representing the fluid transfer.
Right, and they even verified this component, didn't they? Which really gives us confidence in the model's accuracy. They found that GFEM, with this full wellbore model, produced nearly identical results to a previous GF study that just imposed the flow directly at the fracture entrance. That seems like a strong indicator that this wellbore coupling is robust and reliable, wouldn't you say? It's kind of the proof in the pudding.
Absolutely. It validates that simplification in the coupling approach.
Okay, so this method can handle complex geometries, accurately monitor fluid flow from the wellbore, and even manage computational efficiency. Impressive. But here's the big question. How does the simulation actually decide where and how much the fractures grow at each step? What's the brain of this propagation process?
Right, that's where the propagation criterion comes in. For low permeability materials like shale, which is common in fracking, linear elastic fracture mechanics, or LEFM, is the go-to theory for predicting crack growth. Specifically, they use what's called a regularized Irwin's criterion.
Yeah.
This basically means that a point on the fracture front will propagate if its equivalent mode I stress intensity factor.
Okay, that's a mouthful. What does that mean in simpler terms?
Yeah, it is. Think of it as a sophisticated measure of the stress concentration right at the very tip of the crack. How much force is focused there. And this factor needs to be within a small, predefined range of the material's fracture toughness. Fracture toughness is like the material's inherent resistance to having a crack propagate through it. Its breaking point for cracks.
Got it. So if the stress at the tip gets close enough to that breaking point.
Exactly. If the stress intensity at the tip is high enough, basically overcomes that toughness, the crack will grow. And this leads to what we call the propagation phase, where different points along a single fracture front can advance differently. Imagine the irregular, almost organic growth of an ice crystal. Some parts shoot out quickly, others lag behind. It's similar here. Some points on the crack might advance a maximum amount, others might advance linearly, and some might not advance at all during a given time step, all based on this stress criterion. And to make this efficient, the simulation uses an automatic search for the time step. It's an algorithm that intelligently finds the right time interval for propagation based on linear interpolation and extrapolation. This ensures the simulation progresses accurately and quickly, without wasting computational cycles on steps that are too small or getting inaccurate results with steps that are too large.
Okay, this all sounds incredibly advanced, really sophisticated stuff. How do we know it actually works in practice, though? That these predictions are reliable? Let's look at how Shauer and Duarte verified their methodology with some real-world type problems.
Yeah, they tackled several crucial verification problems. The first one involves simulating 3 parallel penny-shaped hydraulic fractures propagating simultaneously. This setup allowed them to rigorously test the algorithm's ability to handle multiple cracks growing at the same time and influencing each other.
Right, and what was the big takeaway from this first verification? What did they learn that's important for someone doing these kinds of simulations?
Well, the results were quite revealing. When comparing their GFM results to other established methods, the outcomes for a fracture size were pretty similar. That's good validation. However, a really crucial insight emerged. You need a 3D computational domain, the simulated block of rock, that is at least 4 times bigger than the largest fracture radius.
4 times, wow.
Yeah, to avoid what they called considerable boundary effects.
Yeah.
This is a significant practical takeaway for anyone doing these kinds of simulations. It basically means smaller domains can lead to inaccurate predictions. It's almost like the virtual walls of your simulation box start interfering with the physics if they're too close to the action.
Okay, so if you don't make your simulated rock big enough, your results won't be realistic. That's a critical detail that can easily be overlooked. And for their second problem, they explored what happens when fractures don't remain planar, allowing for more complex, mixed-mode fracture shapes. This must be a huge leap from simpler models, right? Trying to capture that twisting and turning we talked about.
Absolutely. This problem simulated similar initial conditions, but explicitly allowed for modes 2 and 3 of fracture propagation. These modes account for shear and tearing motions, which inherently lead to non-planar growth, things getting twisty. And this is where the GF really shines, because older methods struggle immensely with this kind of complexity. The discovery here was truly impressive. The interaction between the fractures themselves, combined with the anisotropy of the in situ stresses.
Meaning the stresses in the rock were different in different directions.
Exactly. That combination led to highly complex, almost beautiful, petal-like final fracture geometries. These were intricate, almost organic shapes you wouldn't intuitively predict. And the GFM results showed excellent agreement with boundary element method results, even in these incredibly complex scenarios.
Yeah.
That really proved its accuracy for non-planar growth.
It's like predicting the precise, chaotic patterns of a shattered pane of glass, but underground.
That's a good analogy, yeah.
Okay, now for what I think is the most groundbreaking part, looking at scenarios that are common in practice but have rarely been modeled in full 3D detail. What happens when the initial fractures are not aligned with the natural stresses already present in the rock? This feels like a situation where simplified models really start to break down and could give misleading results.
This is indeed a novel problem in the literature, which makes these findings particularly exciting and practically relevant, very relevant. They set up simulations with 3 parallel penny-shaped fractures, but crucially, they varied the relative angles. They used the symbol gamma between these initial fractures and the horizontal stresses. They looked at Connell-Haby degrees, so perfectly aligned, then 5 degrees and 10 degrees misalignment. And they also explored 2 fracture separation cases, 3 meters apart and a closer 1.5 meters apart. This let them see how both misalignment and proximity affected propagation.
Okay, so what did they find? Was it straightforward?
Not at all. The findings were quite non-intuitive. For perfectly aligned fractures, the 0-degree case, the lateral fractures elongated in one direction, while the middle fracture elongated in another. That's due to the stress contrast effect we've seen before, the stress shadowing. But with misalignment, say 5 degrees or 10 degrees, the lateral fractures primarily propagated away from the middle fracture. They sort of veered off. And the middle fracture, in turn, became even more elongated and developed a wavy profile, almost snake-like, instead of a clean linear extension. Really different shapes.
Wow. And did this affect the pressure needed?
Yes, profoundly. A consistently higher initiation pressure was observed for the more misaligned cases, particularly at 10 degrees. It simply took more force, more pressure to get the fracture started and keep them propagating when they weren't aligned with the natural stress field.
That's really fascinating. So it's not always a straightforward relationship. You're saying that sometimes very different initial alignments could result in similar pressure profiles, but then lead to drastically different final shapes. And other times, the pressures themselves varied wildly depending on that initial tilt.
Precisely. It highlights the complexity. And here's a specific, truly unexpected aha moment they found. For the closer fractures, the ones only 1.5 meters apart, remember?
Yeah.
The typically higher pressure you'd expect in the middle fracture, which usually occurs due to that stress shadowing from the adjacent fractures, was actually alleviated in the misaligned cases, the 5 degrees and 10-degree ones.
Alleviated. How?
It happened because parts of the lateral fractures actually arrested, meaning they stopped propagating in certain directions. This reduced their interaction effect on the middle one. So the misalignment, counterintuitively, made things slightly easier for the middle fracture in terms of pressure, even though the overall initiation pressure was higher. This really showcases the intensely non-intuitive behavior that only a full 3D model can capture and predict.
That's incredible.
Yeah, what seemed like a simple problem of alignment turns out to be this complex dance of stress fields, where a small change, a few degrees of tilt, can lead to dramatically different outcomes in both shape and pressure.
This truly demonstrates why a fully 3D methodology is absolutely necessary. You need it to quantify these complex processes and make informed decisions in the field, relying on simpler, potentially misleading 2D models.
Well, it seems risky. It's like trying to understand an entire chess match by only looking at the pawn movements, as you said.
Exactly. You miss the crucial interactions and the bigger picture.
Wow, this has been an incredibly insightful deep dive into the complex world of hydraulic fracturing simulation. It really highlights how much is going on beneath our feet that we just can't see, and how clever engineering and simulation are helping us unveil it. Indeed. What Shauer and Duarte's 3D GFM provides is a robust, accurate, and remarkably efficient tool. It's truly a leap forward. It's capable of simulating the simultaneous propagation and interaction of multiple hydraulic fractures, even when they're coupled with wellbore flow and encounter these highly complex 3D non-planar geometries. And this capability is absolutely critical for moving beyond that nearly 30% inefficiency we discussed right at the start of this deep dive.
Right. So for you, our curious listener, let's just quickly distill the key takeaways from today's deep dive. Firstly, the intricate, unseen 3D behavior of fractures, profoundly influenced by natural stresses and the interactions between fractures, is a major factor in how efficient or inefficient hydraulic fracturing actually turns out to be. It's not simple down there. Secondly, advanced computational methods like this GFEM are truly bridging the gap between simplified assumptions and that complex, messy, real-world geology. They're allowing us to accurately predict and understand these intricate processes with unprecedented detail. And finally, even subtle changes, like the initial alignment of fractures with the rock's natural stresses, can lead to significant and often very non-intuitive impacts on how fractures grow and how fluid pressure behaves. This all absolutely demands sophisticated analysis and models if we want to truly optimize our energy extraction and reduce waste.
And maybe this raises a final provocative thought. Given the complex, non-intuitive behaviors revealed by these 3D simulations in hydraulic fracturing, what other subsurface engineering processes, think about carbon sequestration or geothermal energy extraction, or even understanding earthquake mechanics, might be hiding similar complexities? Complexities that maybe only these kinds of advanced computational models can truly illuminate. What further questions does this raise for you about optimizing resource recovery or just understanding geological dynamics as we continue to push deeper into the Earth?